Question 2, part A, a couple of definitions required here. We are reminded that Prim's algorithm finds a minimum spanning tree for a connected graph, and then we have to explain what is meant by, first of all, tree, and then what is meant by a spanning tree. Now, these definitions simply need to be learned. The definition of a tree is a connected graph with no cycles. Just going to take a moment to try and demonstrate what that means. So first of all, a connected graph. Well, here I'm drawing some edges. I'm not drawing the nodes just to save time. And let's suppose that is my graph. So that there is an example of a graph. I think I will put some nodes on just to make it look clearer. So this is an example of a graph. And normally we'd see letters on the nodes perhaps, possibly some numbers on the edges. This is not, however, a connected graph because it's impossible to travel from either of these two vertices, which I'm now going to call A and B. It's impossible to travel from either of these to any other part of the graph except themselves. So for example, if I call this one C, it's impossible to travel from A to C or from B to C on this graph. So this graph here is not connected. If I add one more edge, for example, from A down here, this graph is now connected because it is possible now to travel from A to C. So this is now an example of a connected graph. Does it have any cycles? At the moment, no. This graph has no cycles. If I add one more edge, for example, there, this is now a cycle or a circuit. Cycle and circuit mean the same thing. This is what we're looking for. That is an example of a circuit or cycle. So if I take off that last edge, it goes back to having no cycles whatsoever. So this is an example of a tree, a connected graph with no cycles. Moving on now to a spanning tree. What do we mean by a spanning tree? Well, the definition of a spanning tree is a subgraph of a graph, which includes all the vertices of the original graph and is also a tree. So subgraph of a graph. I'm just going to quickly draw an example of a graph here. It doesn't have to be a tree. So this here has quite a few cycles in it. This is just an example of a graph. And I'm quickly going to put on some nodes. So there. There we go. That's just an example of a graph. It's definitely not a tree. It's got a lot of cycles. I'm now going to draw a subgraph of this graph. In fact, I'm going to give this one a name. Let's call it graph capital G. So that whole thing I'm calling capital G. A subgraph of this is simply a selection of those edges and nodes from the original. If we have a spanning tree, then it must include all the vertices from the original graph. So let's get all the vertices on first. So my subgraph must have all the vertices from the original. So 1, 2, 3, 4, 5, 6, they're all there. So already I technically have a subgraph. It just doesn't have any edges. A spanning tree must include all the edges and must also be a tree. So now I'm going to select some of these edges until I have a tree. So let's select that one, and that one, and that one. I'm fairly randomly selecting these here. I could select slightly different ones. At the moment, I definitely don't have a tree because it's not connected. It's impossible to travel from this edge to anywhere on the other part. So at the moment it's definitely not connected, it's not a tree. Now I'm going to choose this one next. And now I need just one more edge. Either that one, or that one. I'm just going to choose the middle one. I could have chosen any of the three, and then I would have had a spanning tree of the original graph. So this here is just one example of the spanning tree of this original graph, which I called capital G. So a spanning tree is a subgraph of a graph, which includes all the vertices of the original graph, and it's also a tree. And from part one, remember a tree is a connected graph with no cycles.